Okay, so we're going to pick up 5.4 and the fundamental theorem of calculus. So, first thing we need is we need f to be continuous on a closed interval. So if f, that is capital letter F of x, is defined as the integral from a to x of f of t dt. So in other words, this is a is a constant, and then we have this variable x. Okay, so just basically saying that f of x is equal to the antiderivative of f of x. So then, if we were to do the derivative of the antiderivative, we get back what we started with. So when we take the derivative of the antiderivative equals our original function. Okay, so here's our y. Again, y is defined as the integral from 0 to x of 1 over 1 plus t squared dt. So this, is our original function. Or in this case, we'll say f of t. So we basically take, so when I want to do dy dx, so we're taking d dx, basically all we have to do is take the x and plug that in for t, so we end up with 1 over 1 plus x squared. Now the next one is going to look very similar. The only difference is this time the lower bound is negative pi. But again, as long as that's a constant, we don't care, it's fine. So when we do the derivative of the antiderivative from negative pi to x of cosine of t dt, we just get cosine of x. There's no plus c, none of that, because we're doing the derivative of the antiderivative. Now, you're wondering how this works, okay? Let's say we went the long way. Let's say we did this problem by actually finding the antiderivative. So what's the antiderivative of cosine? That's sine. And we want to evaluate this from negative pi to x. So we have sine x minus sine of negative pi. Now remember, our goal for these is finding dy dx. So I'm saying now take the derivative of that result. Now sine of negative pi, that's the same as sine of pi, which is really 0. But let's just leave that here, because remember, that's always going to be a constant. So when I do the derivative of sine, I get cosine of x, and then that'll be plus 0 because the derivative, remember, this is always going to be some constant if I'm evaluating it at a real number. So we get to skip all of that process. So this is really the long way, which we don't need to do. When we do the derivative, the antiderivative, as long as the upper bound is a variable and the lower bound is a constant, we can apply the fundamental theorem of calculus. Now the next ones do have a lower bound. Both of these have a lower bound that is a constant, but the upper bound is not just x. For example, in A it has an x squared, and in B there's a negative 2x. So what we end up having to do here is the chain rule, and the chain rule gets applied to the exponent. So let's take a look at what happens. So we end up taking the x squared. Okay, so similar to the last one, when we do the derivative, we're going to replace t with the upper bound, which is x squared in this case, times the derivative of the exponent, which is 2x. So I just get 2x cosine of x squared. Again, we don't care about the lower bound. We just know that we can apply this if the lower bound is a constant. So now let's take a look at the next one. So dy dx. So instead of u to the third, I'm going to plug in negative 2 to the third minus 5. And now I want to multiply the whole thing times the derivative of negative 2x, which is negative 2. So here I get a negative 8x to the third minus 5 times negative 2, so I get 16x to the third plus 10. Now the next one, we have to rewrite this. So if you notice the constants on the top and the variables on the bottom. So before I even do the derivative, I'm going to make that a negative and I'm going to switch the bounds. Now, if we look at this one, we ask ourselves, does the chain rule need to be applied? And the answer is no, because it's just an x as our upper bound. Now I still have that negative out in front, so I'm going to leave that. So it's going to become negative 3x sine x. And that's it. Now, in part B, we have a problem because both the upper and the lower bounds have variables in it. So before I do anything, I want to break this up into two separate integrals. So what I do, we know by the additivity property, we can break up two integrals as long as this upper bound and this lower bound have the same number. So I'm going to break it up like this. Now, I chose 0, but it's really irrelevant what constant that I choose. This will always work out. You can pick it, you can make it 100, you can make it negative pi, you can make it any real number you want. Generally, we just use 0 because it's easy. Now, I noticed that once I broke it up into two separate parts, I now have this 2x on the bottom. So again, I'm going to rewrite this by changing the sign to negative because I want to have the bottom as a constant. And now I want to do the derivative. So I have to do the derivative of each part separate. Now notice in each case I'm going to have to apply the chain rule. So, and I have a negative, so I have negative e to the 2x times the derivative of 2x, which is 2, plus, then we have e to the x squared times 2x, because that's the derivative of x squared. So I have negative 2e to the 2x plus 2x e to the x squared. No reason to simplify that any further. Okay, so the next part, the fundamental theorem of calculus, we actually saw in the last section. This is basically where we evaluate the antiderivative at the upper bound minus evaluating at the lower bound. So we are going to integrate. So we're going to find the antiderivative. So 4 becomes 4x. Remember, we take x to the 0 power. And then plus, that's going to be 2x squared over 2, so that just becomes x squared. And we want to evaluate this from 4 to 6. So we have 4 times 6 plus 6 squared. And we want to subtract 4 times 4 plus 4 squared. And while we evaluate this, double check your work, but we should get 28. Okay, next one. So the antiderivative of e to the x is e to the x, and we want to evaluate that from -1 to e. So we have e to the e minus e to the -1. So we have e to the e minus 1 over e. And again, you could plug that into your calculator, but exact answers are just as good, if not better. Okay, next one. So x to the third becomes x to the fourth over 4 plus x. And we want to evaluate that from -1 to 3. So we have 3 to the fourth over 4 plus 3. And then we have -1 to the fourth over 4 plus a -1 or minus 1. If we take a moment to simplify that, we should get... Okay, so we get the next one is x to the 5/2 over 5/2, so that's multiplied by 2/5, evaluated from 0 to 4. So we have 2/5, and that turns into the square root of x to the 5th. So I have 2/5 square root of 4 to the 5th, and then substituting in 0 just gives us 0. So we have 2 to the 5th is 32. So times 2, we get 64 over 5. Next one, we have the antiderivative for negative sign is the opposite of negative cosine, so that becomes positive cosine of theta from pi over 6 to 5 pi over 6. So we have cosine of 5 pi over 6 minus cosine of pi over 6. Cosine of pi over 6, 5 pi over 6 is -√3 over 2 minus, and then we have cosine of pi over 6 is √3 over 2, so we get -√3. Now the next one, we haven't learned the, this is a composition of functions, and we haven't learned what's called u substitution yet. So what we want to do before we integrate is just multiply that out. So that becomes x squared plus 2x plus 1. Okay, so now we'll integrate. So we get x cubed over 3 plus, so that's going to be 2x squared over 2. So that becomes x squared plus 1x. Okay, so the upper bound, if we evaluate, that's just going to be 0 minus, now we plug in -1, so it'll become -1 to the third over 3 plus -1 squared plus -1 or minus 1. So I have a -1 third plus 1 minus 1. So the opposite of -1 third becomes positive 1 third. Okay, so sometimes we want to find the area between a particular curve and the x-axis. Now we know when a graph goes below the x-axis, right, this area, right, that integral would be a negative. So what we would want to do is, if we want to kind of figure out the area between the curve and the x-axis, we just want to make sure that that region stays positive. So we want to partition it. We would want to make certain from, let's say this is A to B, we would want to make sure that we take the absolute value. So in this example, we have a parabola, and it goes, we want to look at specifically from -2 to 2, and right here and here, so at -1 and at 1, that region is going below the x-axis. So what we want to do is we want to break it up basically 3 different integrals. So the total area, so this will go from -2 to -1 is 3x squared minus 3 dx. I don't need absolute value around here because it's automatically going to be positive. However, the next region, from -1 to 1, I want to put that result in absolute value. So there we go. And then the last part here, that part, I do not need absolute value because it's above the x-axis. So if you were to do it by hand, this is how you would break it up into 3 different parts. And so I would have x cubed minus 3x. Notice all of these are all going to be the same. Okay. So when we evaluate this whole thing, take a minute to verify, but you should end up with 12 is the total region. However, we can also solve this on your calculator. Now, when we do it on your calculator, you're going to do the math. You're going to do 9. So you're going to come up with this. Okay. So this is on the TI-83, or the old version of the TI-84. That's what will show up. Otherwise, it will show up with your integral sign. So we're going to use the same bounds. It's going to go from -2 to 2. But then you want to go to your absolute value. So you're going to go to I'll show you one here. So we'll go math 9, -2 to 2, and then we'll go back to the math, go over to number, and we want number 1, absolute value, and then you'll just type in the function 3x squared minus 3 dx. And we get 12 there also. So if you put the whole thing in absolute value, that also has the same effect. So you should get 12. Okay, so for homework, oops. You should be working on assignment 36, so page 302, 1 to 19 odd, 27 to 35 odd, and so on. And again, you're going to use the rules. You're going to use the rules that we covered, and hopefully I will be back the next day, and we will review. We'll have another day to review this section before we start reviewing for the test. And if you have any questions, you can go ahead and email me.